This is the 8th lecture in the course Signals and Systems, and today's topic would be systems described by differential and difference equations. We had already started the topic of differential equations in the last class, and we had been considering an example of a system described by a first order differential equation y dot plus twice y equal to x. Of course, they are all functions of t. And we showed that if we have an x of t which is of the form k cosine of omega 0 t, then the total response of the system is given by y of t equal to y0 e to the minus 2t plus k divided by square root of 4 plus omega naught squared cosine of omega naught t minus theta, then minus cosine of theta e to the power minus 2t multiplied by u of t. Is that correct? Okay. Where theta is tan inverse, what was it? Omega 0 divided by 2. Is that correct? Theta is this. And we had argued that since a linear system requires 0 input producing 0 output, the only condition under which 0 input can produce 0 output is that this constant y0 must go to 0 for linear system, because if the input is 0 then k is 0 and therefore the whole thing drops out. What only thing we are left with is y0 e to the minus 2t, and it should not have an existence when the input is equal to 0 if the system has to be linear. Now this means that the initial condition y0, you recall, y0 was equal to y of 0. It's the initial condition. Initial condition must be 0. That is, the system, although a dynamic system, must be relaxed at t equal to 0. It must not have any storage of values. We next consider the same system y dot plus 2y equal to x. The same system, we find out whether it is causal or non-causal, and as you shall see, this requires a little deeper thought and analysis. We assume that the system is linear, which means that y0 is equal to 0. We also recall the definition of causality. A system is causal if and only if x1t leads to y1t and x2t leads to y2t. There are two inputs and there are two separate outputs. We know that the system is causal if and only if x1 equal to x2, t less than equal to t0 implies, that is, if the two inputs are identical for t less than equal to t0, that is from minus infinity to t0, then this should imply that y1 equal to y2 for the same interval of time, that is t less than equal to t0. This is the condition, necessary and sufficient condition for causality. We shall try to apply this condition to find out if the system with linearity condition, that is y0 equal to 0, if the system is causal or non-causal. And for that purpose we consider two inputs. One is 0 for all t. Alright, we consider an input which is 0 for all t. Now this implies that since we have assumed that the system is linear, this implies that y1 of t, the response should also be 0 for all t. Agreed? Alright, this is one of the inputs. The second input that we consider is like this. We have a unit step occurring at -1. This is my t-axis and this is 1. In other words, this means that x2t, the second input, is 0 for t less than -1 and is equal to 1 for t greater than -1. Let us calculate the outputs. Alright, let us calculate the output y2t and then verify whether the system is causal or non-causal. Alright. You notice here that x2t is 0 till t equal to -1. So t0 here is -1. If the system is causal, then y2t should also be 0 till t equal to -1. Is that clear? That follows from the definition. Our first input is 0, so y1t is 0 for all times. Second input is 0 till t equal to -1. So if the system is causal, then y2t should also be 0 till t equal to -1. Let us see if this is true or not. You recall that our equation is y dot plus 2y equal to x of t. If I consider, as usual, it has two solutions, the particular solution and the homogeneous solution. Now for t greater than -1, let's consider the solution. T greater than -1, x of t is equal to 1, and therefore the particular solution yp must also be a constant. Since the input is a constant, this is also y, and which means that twice capital Y should be equal to 1 or y should be equal to half. So this is the particular solution. And the homogeneous part of the solution, you already know, yh of t shall be of the form a e to the power some constant a e to the power -2t. Alright, and therefore the total solution for t greater than -1 is given by a e to the power -2t plus half, the particular solution, where the constant a is to be determined from the initial condition, that is at t equal to 0, y equals to 0, and therefore 0 is equal to a plus half, which means that a is equal to -half. Thus the total solution for t greater than -1, total solution is given by y of t. Y of t is equal to a was equal to -half, so it would be half 1 minus e to the -2t. Is that correct? This is the solution for t greater than -1. Now let's see the solution for t less than -1. T less than -1. T less than -1, x of t is 0, and therefore the solution must be of the form, the right hand side is 0 in the equation y dot plus 2y. This is the equation, and the equation has the same type of solution, that is, it is some constant b multiplied by e to the power twice minus twice t. Alright, to be able to evaluate b, you notice that at t equal to -1, the two solutions must be equal, and therefore at t equal to -1, you see, we have already utilized the initial condition once. We cannot utilize it again. Isn't that right? We cannot utilize it again because we have already used it to evaluate one condition. But the continuity of the output, that demands that b e to the power 2 small t is -1. This should be equal to half 1 minus e to the power t is -1, so again e to the power 2, which means that b is equal to half e to the power -2 minus 1. Is that correct? We divided by e squared, and therefore for t less than -1, y, which shall now be called y y2 of t, you recall this is the response to x2 of t. y2 of t for t less than minus 1 is equal to half e to the minus 2 minus 1 and then e to the minus 2t. Agreed? Now you notice that this response y2 of t equal to half e to the minus 2 minus 1 e to the minus 2t, and what was our y1 of t? This is the response for an x of t which is like this, that is at minus 1 it is plus 1 and for all other values it is 0. T greater than minus 1 it is, this is my x2 of t, and x1 of t was 0 identically, which produced an output of y1t equal to 0. Alright, you notice that for this range, that is up to minus 1, up to small t equal to minus 1, x1 and x2 are identical. x1t is equal to x2t for t less than equal to minus 1. Well, let me not put equal to because at minus 1 there is a discontinuity. If the system was causal, then y1 of t should have been equal to y2 of t for t less than minus 1. This is not the case here. That is, it is not the case, and therefore the system is, the conclusion is the system is non-causal. Now the question is, do we have to do this every time we get a differential equation? No, that's not necessary. I went through this exercise to be able to impress upon you the difficulty of finding out whether a system governed by a differential equation is causal or not, and to find out or to explore a method to come out of the difficulty. To come out of the difficulty, you see, the basic problem here was that we assumed y0 equal to 0. Now, and one of our inputs became non-zero before t equal to 0. Alright, one of our inputs x2 became non-zero at t equal to minus 1. That is the problem. Suppose I restructure the problem. That is, I say that x of t, x1 of t was equal to 0, all t. Suppose my x2 of t was equal to 0, no, that's not what I want to say. What I mean to say is, even with this x2 of t equal to 0 for t less than minus 1 and is equal to 1 for t greater than minus 1, even with these inputs, two inputs, well, one of the outputs is y1 t equal to 0 all t, and this output we have already found out under the condition that y2 of 0 is equal to 0. Suppose we had imposed the condition that y2 of t is equal to 0 for t less than minus 1. Suppose we had imposed this condition, that is at all t less than minus 1 the output is 0. Is this system causal then or non-causal? Causal, because y1 of t and y2 of t are 0 till t less than minus 1. Now this is an imposed condition, that is for all values of t less than minus 1 it is 0. Now this will be satisfied in terms of the solution to the differential equation. We do not require such a condition. What do we require? We require a spot condition, just one condition, because you have to evaluate one constant. We don't require for a continuum from minus infinity to minus 1. We don't require this. but we have imposed this in order to bring causality. In terms of the differential equation, what is it that we need? We only need that y2 of -1 equal to 0. And I leave it to you as an exercise to solve the same equation not under the condition of y0 equal to 0, but under the condition that y of -1 equal to 0. And you can easily show then that y2 of t identically equals to 0 for the continuum from -infinity to -1. In other words, one is equivalent to the other. The moral of this exercise is that for a linear system, now we shall prove it formally. For a linear system, causality demands, we state it in the form of a theorem now. For a linear system, causality demands that if x of t equal to 0 for t less than t0, then y of t must be equal to 0 for t less than t0. And we shall show that this condition is both necessary as well as sufficient. In other words, you do not have to test for two inputs, x1 and x2. One input suffices. X of t, if x of t is 0, if the input is 0 from -infinity to t0, then the output should also be 0, identically 0 from -infinity to t0. And we shall show, since it is stated in the form of a theorem, we shall show that this condition is both necessary and sufficient. Alright, it's very simple and very simple to show, but this is a simplification of causality test for a linear system. If the system is not linear, then this theorem is not valid. The emphasis is on linearity. This is true only for a linear system. Let us show this. Showing this would be quite simple. If the system is linear, S is linear, then you know that x of t equal to 0 implies that y of t equal to 0. And therefore necessity is trivial. Necessity means if x of t equal to 0 for t less than t0, then linearity demands that as long as x of t is 0, y of t must be 0. Alright? Necessity is trivial. Since the system is linear, 0 input must lead to 0 output. And 0 input stays up to t equal to t0. So up to t equal to t0, the output must be 0. Y of t must be 0. Now, let's consider sufficiency. Is this a sufficient condition? In other words, we assume that this is true. Then we show that the system is causal. And that proof is constructed in a little different manner. What we do is, we say that x12 t leads to y12 t. Alright? And we say that x1 t is equal to x2 t for t less than t0. Then we know that if the system is causal, then y1 t must be equal to y2 t for t less than t0. Alright? This is the strict test for causality. We take two inputs, x1 and x2. If they are identical till a certain time t0, then the output should be identical till that time t equal to t0. Alright? So we take two inputs. To show sufficiency, we take two inputs, x1 and x2, and we constrain such that x1 and x2 are identical till t equals to t0. Then we apply a trick. We say, let's apply, the system is linear, let's apply x1 of t minus x2 of t to the system. Then since the system is linear, the output must be y1 of t minus y2 of t. Alright? Till t is equal to t0, the two are identical. x1 is identical to x2, and therefore the left hand side means we have applied a 0. So the output must be 0. There is no other way. Output must be 0, which implies that y1t is equal to y2t. Is the proof clear? There is a slight involvement here. You must realize this. What we have done is, we have taken the strict condition. Then we have applied linearity condition. This is not true. This is not true unless the system is linear. Alright. What we have done is, we have said, okay, alright, we take two inputs, x1 and x2, which are identical till a certain point of time. They may differ t greater than t0, and let the outputs be y1 and y2. Then we superimpose the two. That is, we apply x1 minus x2 and bring in the constraint of linearity, linear system. Therefore, the output must be y1 minus y2. Then we say, let t be less than t0. Since t is less than t0, x1 and x2 are identical, so the left hand side is 0. It must produce a 0 output. If it produces a 0 output, then y1 must be equal to y2 till t equals to t0, and therefore the system is causal. So, in future, if you want to test a linear system for causality, you can either do this, you can either take two inputs x1, x2, which are identical up to a certain point of time, find out y1 and y2, show whether they are equal or not, or you can apply the equivalent condition, that is, a linear system, a linear S is causal if and only if an input x of t which is 0 for t less than t0, less than equal to t0, implies y of t equal to 0, t less than equal to t0. In other words, the output must follow the input provided it is 0, not a non-zero value. xt equal to 0, t less than t0 must imply that yt, the output, cannot occur before the input attains a non-zero value. That's what it means, causality. Alright. We next consider the question of time invariance. Time invariance. And we state the result first, rather than deriving this, and we shall demonstrate that it is so. A linear causal system is necessarily time invariant. A linear causal system is also time invariant. That is, if you can guarantee that the system is linear and the system is also causal, then it is necessarily time invariant. Now we shall demonstrate this. But before we do that, I want to introduce a term. This causality of a linear system, you recall, we required that if x of t equal to 0, t less than t0, demands that y of t equal to 0 for t less than t0. Now, y of t is the output of the system, and this condition is known as the condition of initial rest. I want to introduce this term. Initial rest. Initial rest means that till the output becomes non-zero, till the input becomes non-zero, x of t becomes non-zero, the output must sleep at rest. the output cannot rise to a non-zero value. This we shall, instead of writing this again and again, we will say the system is at initial rest. And most of the techniques of system analysis that we shall study shall assume this condition. That is, we will assume that the system is linear, causal and time invariant, or we shall say it is linear and with initial rest. If there is initial rest, it implies causality, it also implies time invariance. Let's demonstrate that a system at initial rest is indeed time invariant. And the demonstration is extremely simple. Let's consider the same example, that is y dot plus 2y equal to x. And suppose we apply an x of t, suppose we apply an x1 of t, which is 0 till some time t0. Till some time t0, it is 0, and then maybe it falls down exponentially. Suppose x1 of t is like this. Alright, and the system is causal, and therefore y1 of t, the output, must also be equal to 0 for t less than t0. We assume that the system is linear and causal. We are investigating its time invariance or time varying property, whether it is time invariant or time varying. Alright. Now let's delay the input. How do we test time invariance? We take x1 of t, then we take another x, that is x2 of t, which is a delayed version, let's say x1 of t minus capital T, which is a delayed or advanced version of the input, and we try to see whether the output shape remains the same or not, and whether the output delays or advances by the same amount or not. To recall the definition of time invariance, the system is time invariant if x1 of t leads to y1 of t and x1 of t minus tau leads to y1 of t minus tau. Alright. So what we do is we delay the input by an amount capital T. Then if I plot x2 of t versus t, this shall rise at a time which is equal to t0 plus capital T, and the system has already been assumed to be causal. That is, the system is at initial rest, the term that I introduced, which means that the output of this y2 of t is equal to 0 for t less than t0 plus t. Agreed? Since the input is 0 till t0 plus t, the output must be 0 for t small t less than t0 plus t. And you can now easily verify that y dot plus 2y equal to, well, y2 dot plus 2y2 equal to x2 with y2 t equal to 0, t less than t0 plus t is satisfied by y2t. This equation is satisfied by y2t equal to y1 of t minus capital T. All you do is substitute for x2, it is t minus capital T, then bring back x1. You will see that y2 becomes identical to y1. It's a trivial manipulation. I would like to skip this. Now, we have talked only of the first order differential equation. What about the general differential equation? A general differential equation can be written, a general constant coefficient differential equation can be written like this: ak, some constant, dky t dtk, where k goes from, yes, what is the lower limit? 0. If k is 0, there is no differentiation. In other words, it is the yt term. We shall have simply a0 y of t to, let's say, capital N. All right. This is the combination of outputs and their differential coefficients. Capital N number of differential coefficients are involved in this expression, and if this is equal to some combination of input and its differential coefficients, that is, let's say bk dkx of t dtk, where k goes from again 0 to some value. It is not necessarily equal to capital N, some value capital M. Capital M can be greater than, equal to, or less than capital N. Alright. However, the order of the system is determined by capital N. That is, if capital N goes up to 0, that is, there is only one term, then in the left hand side you shall simply have y of t, a0 y of t. The order of the system is 0, that is, it is a static system. Even though differential coefficients of the input are involved, the order of the system is 0. Similarly, if capital N is equal to 1, we call it a first order system, and we have already seen an example of a first order system, y dot plus 2y equal to x. In general, therefore, this equation represents an nth order system. Nth order system. And you know that to be able to solve an nth order system, you require n initial conditions. You require n initial conditions. Now, in the literature, one distinguishes between initial conditions and auxiliary conditions. Initial condition term arises from the fact that usually the conditions are stipulated at t equal to 0, and therefore they are called initial conditions. It can be shown that t equal to 0 is nothing sacred. You could specify the conditions at some time t equal to t1, which could be positive or negative, and therefore one distinguishes between what are known as auxiliary conditions. Alright, so we will in general say n auxiliary conditions. These auxiliary conditions could be initial conditions or may not be initial conditions. Sometimes loosely we shall use the two terms interchangeably. When we mean auxiliary conditions, we may speak of initial conditions, but it should be clear in the context. These conditions are on y, y dot, y2 dot, up to y of n minus 1 dots. Alright, we require capital N number of initial conditions. You see, without dot, this is 1. So the order of differential coefficients needed at a certain point of time t equal to t1 are capital N. The order of differentiation is n minus 1, 1 less than the order of the system. And it can be shown, we will not show this. Now I am trying to generalize. You saw that y dot plus 2y, that is a first order system, was linear only when y0 was equal to 0. Alright. It can be shown that an nth order system governed by a linear differential equation is linear if and only if all the auxiliary conditions vanish. That is, the system is at initial rest. Now, initial rest here means not only that y of 0 or y of t1 equal to 0, we must have y dot t1 equal to 0, we must have y2 dot up to y of n minus 1. And here the term initial rest assumes a new interpretation, that not only its value is 0, but its differential coefficients are also 0. Alright, we will also state without proof the condition for an nth order linear system, nth order linear system to be causal. What is the condition? We have already proved it. When we proved that x of t equal to 0, t less than t0 should imply a linear system is causal if and only if a linear system is causal if and only if x of t equal to 0, t less than t0 implies that y of t equal to 0, t less than t0. Did we consider a specific order of the system? No. We considered a general system. So a general nth order linear system is causal if and only if xt equal to 0, t less than t0 implies that y of t equal to 0 for t less than t0. This is a simplification, as I have already mentioned. You do not have to take two specific inputs. One input suffices. All that you have to test is, in the range that xt is 0, is the output 0. If it is not, then it is non-causal. In a similar manner, we can talk of difference equations. Naturally, difference equations characterize discrete time systems, and a typical example of a difference equation or a system described by a difference equation could be something like this: yn minus half y of n minus 1 equal to, let's say, x of n. This is a typical difference equation. In such an equation, the present value of the output is combined with some of the past values. We are considering a causal system. Some of the past values of the output, the present input, and perhaps we might have some past outputs also. Let's say, for example, 1/3 x of n minus 2. The order of such a difference equation, order of a system described by such a difference equation, is simply the number of differences that are involved in y, that is the output. In exactly the same manner as in continuous time systems, the order of the system was equal to the order of the differential coefficient needed. Here, the order of the system is equal to the order of the differences in the output required to write the difference equation. Here, for example, the order is equal to 1. If I write y of n as, let's say, ak, x of n minus k, let's say k equal to 0 to capital M, an equation like this describes a zero order system. Although there are differences of the inputs involved, that does not characterize the system order. System order is characterized by the number of differences required in the output. The general equation to a discrete time system in terms of difference equation is of this form: ak y of n minus k, k equals 0 to, let's say, capital N, is equal to summation bk x of n minus k, k equals 0 to, let's say, capital M. This is an nth order system. Alright. Now if the simplest case can be that n equals 0, simplest case, a zeroth order system for which you can write y of n, it's very easy to show that it's equal to y of n is equal to bk by a0, k equals 0 to m, x of n minus k. Alright. This is a zeroth order system, and if you compare, well, there are two things in this equation to be noted. One is that for computing the present output, we do not require any past output. Alright. In other words, we do not require any feedback. The past outputs have already passed. We shall have to get them from the memory. We shall have to retrieve. If I had a y of n minus 1, I had to go back to the memory and ask for the immediate past output. There is no recursion here, and therefore this equation or this system is called non-recursive. Alright, another adjective that is given to such an equation, such a system, will be obvious if we write this as ck. bk by a0, let's say it is ck. Then I can rewrite this equation as y of n equals to ck x of n minus k, k equals 0 to, let's say, capital M. If you recall the convolution relationship, the convolution was that if I have an x of n, then y of n is given by the convolution of x of n with h of n, the unit impulse response, and the equivalent notation, equivalent summation is k equal to minus infinity to plus infinity x of, well, I can write x of n minus k h of k or h of n minus k x of k. Either way it is correct. So let's write it in the form x of n minus k h of k. If you compare these two, this equation and this equation, then two things are apparent. One is that these ck's are exactly identical to hk's, and therefore the constants occurring in the equation are the samples of the impulse response. So ck equal to hk, and it is directly determined from the given equation. The given equation directly shows samples of hk, so the impulse response is known. Not only that, since the impulse response, since ck's exist only for capital M plus 1 values, from k equal to 0 to plus m, and therefore the impulse response is finite. In this equation in general, hk, k goes from minus infinity to plus infinity, so it is an infinite impulse response. This is a special case of the general convolution relation, and therefore if this is the case, then we say it is not only it is a non-recursive system, it is a finite impulse response system. Finite impulse response system is an extremely important term. It is an FIR system. On the other hand, any system which is not FIR must be IIR, that is infinite impulse response. A system which is not FIR is IIR. Alright, these two terms shall occur many times in future. Now let's go back to the original equation that I wrote, ak y of n minus k summation k equals 0 to capital N equals to bk x of n minus k, k equals 0 to capital M. In general, if n is not equal to 0, then this system of equation, or the system which is described by this equation, produces an output the computation of which requires sum of the past outputs. You can write it in the form y of n, very simple manipulation. You can write it as summation bk by a0 x of n minus k, k equals 0 to capital M, minus summation ak by a0 y of n minus k. That is, you retain only y of n term on the left hand side and shift all the others to the right hand side. Then k goes from 1 to capital N. You notice that to be able to compute y of n, that is the present output, not only you require the input and its past values, but you require some of the past outputs also. And therefore this system requires recursion or feedback. That is, you shall have to ask the memory to give some of the past outputs to be able to compute the present input, and therefore this system or the equation is, the system is known as a recursive system and the equation is known as a recursion equation. Recursive systems are usually IIR. They are usually infinite impulse response, but it is not necessary. Non-recursive systems are usually FIR, usually. So we must distinguish between this. The literature sometimes confuses between the two. Non-recursion and FIR, they equate. Recursion and IIR also they equate, which is not correct. Usually non-recursive systems are FIR. I must qualify this as usually, whereas recursive systems are usually IIR, but it is not necessarily so. In other words, we can have a recursive system which is FIR, that is, an FIR output can be computed in terms of a recursive system. Let me give you a quick example. You recall that this system y of n is equal to x of k, k equal to 0 to small n. You remember this equation. This is a linear system, alright, a linear system in which and it's an invertible system. You remember. Now, would you call this FIR or IIR? Obviously it is FIR. And what are the impulse response sequences? It's unity all the way. What is the total number of impulse response sum? N plus 1. That's correct. So it is an FIR system with h of n equal to 1 for n equal to 0 to h of k equal to 1 from k equal to 0 to n. Alright. Now, it is an FIR system. Is it recursive or non-recursive? Non-recursive. It does not require recursion. It doesn't require past outputs. But you remember that this system, if you want to invert the system, then y of n minus y of n minus 1 equals to x of n. And therefore you could compute y of n recursively. That is, you could write x of n plus y of n minus 1. So one counter example is good enough to shatter a theorem, alright, and therefore we show that a recursive system is not necessarily IIR and a non-recursive system is not necessarily FIR. No, it's the other way around. An FIR system is not necessarily non-recursive. It could be recursive also. Similarly, it can be shown that an IIR system is not necessarily non-recursive. It could be recursive. I beg your pardon, I made a mistake again. Let me state it. An IIR system is not necessarily recursive. It could be non-recursive, and the proof of this shall have to wait till we do fast Fourier transform. FFT is an example of computing computing an IIR system non-recursively. I'm correct. I'm sure I'm absolutely correct. That's all for today. We'll continue this next time.